is vitally important in so many areas of science, but I would argue that it's most important in astronomy. In other sciences, if you're studying chemistry, of course, you can just grab chemicals off the shelf and do an analysis, do an experiment. But in astronomy, we can't go to other stars, for example, to study them. Very famously, Lord Kelvin, in I believe the late 1700s, once they began to realize how far away the stars were, said that we would never learn about the stars because they're so far away. And of course, now in the 21st century, we still haven't visited other stars. But because of the hidden messages in the light, thanks to spectroscopy, we can analyze starlight and know everything about those stars. And that's what this section is about and why it's so incredibly important to astronomy above all other sciences. We need that. We can't go places. We have to be able to analyze the light. And the way we do that is with a spectroscope. A spectroscope takes a beam of light. It passes light through a very narrow slit to create a beam of light, and then passes that light either through a prism or bounces it off of a diffraction grating. A diffraction grating usually consists of a piece of plastic or a piece of glass that has very narrow slits in it. And as the light reflects off the slits or goes through the slits, it breaks it up into a rainbow of colors. Now, the first person to realize that white light consists of all the colors of the rainbow was Sir Isaac Newton. But unfortunately, Newton never discovered the hidden message in the light. He never passed it through a narrow slit to discover these hidden lines in the light. That would have changed history had he discovered that in the 1700s. But as it was, that would have to wait until the 1800s. But anyway, you can actually do this. You can create your own diffraction grating with something like a CD. A CD or a DVD, they contain lots of little narrow slots. And as a laser shines down on a CD, the laser either goes through a slot or it doesn't. And you can set up a binary code that way. If the laser goes through, it's a 1. If it doesn't go through, it's a 0. And you can record data, information that way. That's how CDs work. But anyway, all those little holes in a CD or DVD act like a diffraction grating. And so if you take a DVD and look at it in the light, you'll see a rainbow of colors forming on the DVD. That's all the diffraction grating is. And then we either look at that rainbow through an eyepiece or we run it directly into a computer. That's called a spectrometer when we record the spectrum on a computer. So, what do we see? When you take a narrow beam of light and reflect it off a diffraction grating, what do we see? Well, by the 1860s, Gustav Kirchoff had summarized that you're going to see one of 3 types of spectra. The first type is just a continuous rainbow. That's the one on the top of the screen. I'll move my mouse there. A continuous rainbow, a continuous spectrum. That's really not too important for astronomy. The next one down, the middle one there, you see a black background with colored lines. The one in the middle, that's called an emission spectrum. That is pretty important to astronomy. The bottom one is the most important one, where you have a rainbow background with black lines. I know they don't look black on the screen there, but they're supposed to be black lines. That's called an absorption spectrum. Most things in space will give you that type of spectrum. So let's take them in order. First up, we have a continuous spectrum. What's going to produce that would be something like a solid, for example, that's heated up so much that it gives off light. And it's going to give off white light in the form of a nice smooth rainbow. The most obvious example of that would be a light bulb. Just a regular light bulb filament. A small little piece of metal, usually tungsten or something, that's heated up so much that it produces light in a regular incandescent light bulb. There's a great story about Thomas Edison and how he tried so many different types of filaments because some filaments would burn out too quickly. They might produce a bright light, but they would burn out quickly. And then other filaments would last a long time, but they couldn't produce enough light to light up a room. And so he tried many different light bulbs. And one time a reporter was making fun of him kind of and said that, what does it feel like to fail 10,000 times? And Edison famously replied, Oh, I haven't failed 10,000 times. I've successfully found 10,000 ways that didn't work. So great attitude there and great lesson on perseverance. And so he finally invents just the right kind of filament to last. Anyway, doesn't have a lot to do with astronomy though. An emission spectrum does. This is when you heat up a hot gas. And when you do, you get a black background with colored lines. And the most important part of this is that you always get the same set of colored lines, the same set of spectral lines for each element. Each element has its own set of lines, much like a fingerprint. So if you see those lines present in a star's atmosphere, you know that star has that particular element there. So if it's the lines for hydrogen, then we know that star has hydrogen in its atmosphere. Very, very important, and it proved Lord Kelvin wrong. We can know what the stars are made of without traveling there. Now, in this case, a hot gas could be something like a neon sign, of course, where you're heating up a gas directly. But in space, it would be something like the Orion Nebula. The Orion Nebula has hot stars inside of a cloud. They're being born there. And those hot stars light up the cloud so that the whole cloud acts like a neon sign. It's one reason it's so beautiful and easy to photograph, is because it's being lit up that way. And so the Orion Nebula would produce an emission spectrum. The sun's corona is another example. Only during a total eclipse will the sun produce an emission spectrum, when all you're seeing is that hot gas surrounding the sun, the corona. Here's an example of an element fingerprint that's easy to identify. Sodium has a very distinct fingerprint. It has two yellow lines very, very close together. And that's one that caused a problem to Kirchoff and his partner, Robert Bunsen, Mr. Bunsen burner himself. They were seeing sodium in every spectrum that they did until they realized it was just that their glassware was dirty. Their glassware had sodium from the air all over it. And so they were detecting sodium in everything that they did until they cleaned their glassware properly. So that's an emission spectrum. And for sodium, it'd be two yellow lines. Here are ones that we did in class over the years, all the way back to 2007. You see the old school flip phone there in this guy's hand. And you see the spectral lines. Those are emission lines, spectral lines from a particular element. But even more important in astronomy are absorption lines. This is what we typically see, where you have a rainbow background with dark lines. So there's the first line in the red. If you follow the cursor there, that's the hydrogen alpha line, and then hydrogen beta line and gamma and so forth. So those are always the lines for hydrogen. If you look at the sun, if you look at any star, you're going to see those same dark lines representing hydrogen. And they actually appear in the same exact place that the emission lines appear. So for example, if you had two dark lines right in the middle of the yellow there, that would indicate sodium. They appear in the same place. What's the difference? Well, in this case, for absorption lines, you have a cool gas, not a hot gas. So if you heat up sodium, you get two bright yellow lines if you heat up sodium gas. But if you pass a light through cool sodium gas, you'll get a rainbow background, but two dark lines right at the exact same place in the yellow, two absorption lines. Now, the first person to discover these lines was Joseph von Fraunhofer. He was a glass maker. He was he worked with optics and was actually sort of discovered. He was an orphan, and he was being abused in a factory and all that. He has a very interesting life story. And anyway, he became an expert on glass and on light, and he discovered these lines. He had no idea what they were or what they meant, but it led to a revolution in the 1800s of discovering what things are made of. And look at this, the kind of things in space that give off these dark absorption lines. Oh, nothing too important. Just stars and planets and nebulae. I mean, the vast majority of things that we study in astronomy. So this was an incredibly important discovery by Fraunhofer. Even though he didn't understand all of it, it was going to lead to a revolution. So here's the sun's total spectrum. Check that out. So that kept him pretty busy in the 1800s trying to decipher this code, trying to find all the different elements that were present in the sun and present in the stars. So as a summary here, from Kirchoff, we have a continuous spectrum from a glowing solid like a light bulb filament, not too important in astronomy. Then you have a hot gas like the Orion Nebula producing an emission spectrum. And then you have, when you have a star or a planet's atmosphere, light shining through that atmosphere will produce an absorption spectrum, a rainbow with dark lines. And those dark lines tell us what that nebula or planet or star, what they're made of. And finally, Kirchoff and Bunsen then very meticulously went through and methodically figured out what the elements were in the different stars. They'd heat up something in the lab and match it to a star, other people as well. And they began to realize there were extra lines. They didn't have certain gases in the lab that could match up to lines. And they realized they were discovering new elements. And there were several elements discovered in the 1800s through spectroscopy. Probably the most famous one is the one that they discovered in 1868, looking at the sun's spectrum. So they named this element after the sun. It's a pretty well-known element. Helium. Like Helios or heliocentric theory? Yep, helium was discovered on the sun before it was discovered on the earth. Pretty interesting, huh? So there were no helium balloons. Abraham Lincoln never got to have helium balloons on his birthday. 1868. Today, we get our helium, since the earth doesn't have enough gravity to hang on to helium, it's not in our atmosphere, we actually get it from underground. Usually where they're drilling for natural gas and things like that, they find deposits of helium underground. Places like eastern Texas contain a lot of the world's helium. So just a little trivia there about the element helium. Thanks for listening.